Welcome back. Today we will discuss the topic of what is known as linear inequalities. Over the past 2 weeks, we have discussed how to manipulate linear equations of one variables. We saw that regardless of how complicated a situation you might be faced with, whether it be a multi-step LAOV with nasty-looking equations, or whether it be some sort of exotic circumstance, you will always reduce a multi-step LAV to a two-step LAV, and from a two-step LAV to a one-step until you obtain a solution. Now, it turns out that this thing called a linear inequality is going to build off of our understanding of LEOVs. And so all we're doing when we introduce the notion of linear inequality is we're taking what we know about LEOVs and we're adding some extra steps or some extra details. Okay? So that's the first thing that students should know. Recall back to maybe the 5th grade or 4th grade when you were introduced to what is known as inequality operators. There are 4 inequality operators. There is what is known as a less than, greater than, less than or equal to, and a greater than or equal to operator. And what these inequality operators allow us to do is they allow us to express a relationship between one type of thing and another type of thing. So, for example, I'm able to express this idea that 1 is strictly less than 2, which is to say that if you have 1 stone or $1, that is absolutely less money than having $2. And all else being equal, I would much prefer having $2 over $1. We might, on the other hand, use what are known as conditional inequalities to express this idea that there exists a relationship that has multiple conditions. So, for example, you might say 2 is less than or it's equal to 2. And we would say this is a true statement because 2 is in fact equal to 2. It's not necessarily less than 2. It is in fact equal to 2. So, but nevertheless, because you're using this less than or equal to operator, we can still express the notion that 2 is related to 2 while opening the door that it could possibly be less than 2. Now, 2 is 2, so it will never be less than 2, but in fact, we can relate these 2 numbers together in the following manner. I digress. So, we're able to relate 2 or more math objects to one another using linear inequalities, and when it comes to equations that have linear inequalities built into them, we have very much the same notion. You might have an unknown number plus 2 is strictly less than 10. This inequality expresses the idea that you have potentially a range of different things that could be added with 2, which must remain strictly less than some value, in this instance 10, right? So just as an example of this, you can think to yourself, well, what could possibly be plugged in for x? And, you might think, well, what about the number 4? If we substitute 4 in for x, and we ask ourselves, does the inequality hold? You might say, yes, 4 plus 2 gives you 6. 6 is absolutely less than 10. But what's interesting about inequalities as compared to, say, linear equations is that you don't necessarily just have a single solution for the linear inequality. In fact, you have a range of potential solutions, because while I could have picked 4 for my x value, I could have just as easily picked, say, the number 5 for my x value. And if I ask the question, 5 plus 2 is this strictly less than 10? We would, of course, say, yes, 7 is less than 10, just like 6 is less than 10. 7's greater than 6, but it's certainly less than 10. I could have just as easily picked 6 and asked the question, is 6 plus 2 less than 10? And here again, we would find that this value would also solve the linear inequality. So one thing we should note is that a linear inequality, unlike a regular expression that has an equal sign in it somewhere, or a regular equation that has an equal sign somewhere, will have a range of possible solutions. And when we say a linear inequality has a solution, what we're looking for is we're looking for a statement to hold true, such as this 6 less than 10. This means, this would tell us, because this is a true statement, this means that 4 was the solution to the inequality. When we wrote out 5 plus 2 is strictly less than 10, and we found that 7 is indeed less than 10, we would say that 5 would be a solution to the inequality. And similarly, we would say 6 might be a solution to the inequality, right? So then the question is there potentially an easier way other than just simply guessing what values x could be? Might there be a simpler way to say find all of the solutions or all of the potential solutions? And the answer to that is absolutely. And what we're going to do is not actually that different from manipulating LEOVs. We're going to take whatever inequality we might be given, and we're going to look to, say, use either the additive or multiplicative inverses in order to manipulate the expression so that we can get our unknown value on one side and all of our other terms on the other side. And so in this instance, we've got x plus 2 is strictly less than 10. I'm going to add a negative 2 to both sides of my equal sign. And so I've got 2 plus negative 2, that gives me 0. 10 minus 2 will be on the other side. I get 10 minus 2 gives me 8. X plus 0 gives me x. All right. So you found that x must be strictly less than 8 if we are to create an inequality that actually makes sense. Of course, what do we do with this information? Well, one strategy would be to imagine what's happening in this particular instance. Imagine having a infinitely long measuring tape. Where in the middle of the measuring tape, we're going to pretend that the measuring tape is measuring from 0, and the measuring tape can either measure to the left, going to infinity, or it can measure to the right, going to infinity. And if it's measuring to the right, we'll say that it's measuring to positive infinity, and if it's measuring to the left, it's measuring to negative infinity. Now, if we were to say that x must be strictly less than 8, then somewhere on this number line, I'm going to have the number 8. And what this strictly less than 8 means is that, well, 7 in this instance would be a solution, but so would 6. 6 would be a solution, and 5 would be a solution, and 4 would be a solution, so on and so forth, all the way until you got to 0. But then you would have negative 1. Negative 1 would be a solution. Negative 2 could be a solution. Negative 3 could be a solution, so on and so forth, all the way until you get to negative infinity. These could all possibly be numbers that would satisfy this particular equation. And not only that, but all the numbers in between 7 and 8. So like 7.5 or 7.5, that would satisfy this. 7.6. You could get really, really close to 8, but not be 8. 7.999999999, continuing on to infinity. That would be really, 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 really close to 8, but it's still not 8 exactly. And so, consequently, all of the values along the number line that are strictly less than 8 could be a solution to this particular inequality. And the way we illustrate that that x will never actually be 8 is that we're going to use a parentheses pointed towards negative infinity to represent that x will never be actually equal to 8. Now, students should know that depending on the online source, so if you go online and you look up this particular material, that people online use a variety of notations for doing the math with inequalities. So while the textbook that we use uses the parentheses notation, and it's fairly common for various calculus books to use the parentheses notation, there is in fact another notation that's used and is quite widespread, and that is the open dot, closed dot notation. So for the sake of students just general understanding and being able to follow what's going on if you do pick up another textbook, is that instead of a parentheses, many textbooks will use a open hole to represent the idea that x will never actually touch on the number 8 if you have this strictly less than operator. Okay. Now, there is, in fact, a second way that we might be able to illustrate all of the solutions for this particular inequality, and that is with what is known as the set builder notation. So for the set builder notation, we can imagine all of the possible numbers that we're dealing with as belonging to a big bag, okay? A big bag of items that have certain properties. And we'll denote this big bag of items with the curly braces on both sides. So I'm going to give myself some space. I'll write down 2 curly braces. And for an x strictly less than 8, you might say x, a vertical bar. You'll say x is less than 8. You want to use a comma. You want to say x belonging to the real numbers. Now, the textbook skips an explanation of what's going on here, but basically with a set notation, on the left-hand side, this is the properties or items, sorry, not properties, but items, rather, that you're trying to enumerate. The items that you have in the bag, if you will, or the sets, and then on the right-hand side, this is the properties of the items. So in this instance, what do we have in our bag? Well, we have these individual numbers, which we can denote with x. So x just means some unknown number, and on the right-hand side of the vertical bar, we can denote the properties that this number must have, or that this set, this bag of numbers must have. And in this instance, we can write x must be strictly less than 8. Now, the textbook leaves out this little bit, but this is critical. The R stands for the real numbers, and the E stands for belongs to. So this is critically important because you have to denote in mathematics what type of number you're actually dealing with. You can't just say x less than 8. Well, are you dealing with all of the integers, all of the whole numbers less than 8? Are you dealing with all of the fractions, all of the rational numbers that are less than 8? So on and so forth. You have to denote that, no, I'm dealing with fractions, I'm dealing with integers, I'm dealing with everything in between. And so, for the sake of simplicity, we write x belonging to R. Now, the good news is students will very rarely have to use this set builder notation until they get into more advanced math classes. And you'll have a lot of practice with using set builder notation before you get to those classes. So I'm introducing it here for you to be introduced to the subject, but by no means will I actually ask you guys questions using set builder notation until you get to my Math 1100 course. Just be aware, you will see this again. You're going to see set builder notation in Math 1100. You're going to see it in college algebra. And so be familiar with this idea that, you might be able to represent numbers as belonging to like a specific bag or a specific grouping, and that we have to define what properties of the numbers that we're actually dealing with happen to be. So, that being said, a better notation, which is what we call the interval notation, is to simply use a parentheses to denote this idea that x can never actually be equal to 8, as is the case here. And we'll use another parentheses to denote the fact that x will be going towards negative infinity, or tending towards negative infinity. And so you could equally write a solution as being parentheses negative 8, comma 8. And this would tell me that x can be any number between negative infinity and the number 8, but it will never actually be the number 8. Now, just a little bit of an explanation about negative infinity. Negative infinity is not a real number. And what we mean by this is infinity is a concept. It's a concept for something that's very, very large. And as there exist a number of different types of infinities, as it would turn out, infinity isn't actually that useful as a concept, other than to just say that this is a really, 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 really large number. Okay, there's not much that we can do with infinity, because it's just an idea. You can never actually count up to infinity, right? Like the universe would die before you got done counting all of the things in it. So we use the parentheses that's next to the negative infinity and never a bracket to denote this idea that the negative infinity doesn't actually exist. It's just a concept. It's an idea. Okay? Let's look at another example. Suppose you have x is greater than or equal to 8. And we wanted to denote the interval notation or the solution to x is strictly greater than 8 using a number line. How might we do this? Well, just as before, we are going to draw a horizontal line. And what I like to do is I like to just label negative and positive infinity. I like to put a 0 somewhere on my number line. And then somewhere beyond 0, like perhaps over here to the right, I'm going to label an 8 on my number line. If x is strictly greater than or equal to something, instead of a parentheses at that number, what we're going to use to denote the idea that x could actually be 8 is a bracket. And since x could be greater than 8, the bracket needs to be pointing, instead of towards negative infinity, towards positive infinity, because x could be, say, the number 9. X could also be, say, the number 10, because 10 would be strictly greater than or equal to 8. X could be the number 11, the number 12, so on and so forth, all the way up to positive infinity. And so we represent this idea by shading everything towards positive infinity, but having a bracket at 8. Using the closed hole notation, you may represent the same thing by putting a dot specifically at 8 and shading everything towards positive infinity. Okay? Whether you use the closed hole notation or the bracket slash parentheses notation, it does not matter to me. Just know that both notations are used once you get towards the college algebra and when you go into the calculus sequence. You're going to need to know both of these notations. If we wanted to represent x is strictly greater than or equal to something using the interval notation, what we're going to do is we're going to give ourselves a bracket, and we're going to think that we are starting at this number 8. And as we ascend up the number line, we're ascending towards positive infinity. But positive infinity isn't actually a number. It's an idea. And so we will use a parentheses to denote that you can't actually ever get to 100. I'm sorry, you can't ever get to infinity. And this is our solution. Now you might have nasty looking inequalities such as 4y minus 5 is less than or equal to 3y minus 2. And these kinds of inequality expressions merely require you to do some equation balancing in order to get all of your terms on one side and all of your numbers on the other side. And so in this instance, what you're going to do is you need to decide, do you want to get all of your y values on the left side or on the right side of your inequality? Once you make a decision, you're going to use the additive inverse on both sides of your inequality symbol in order to move the values to the correct side of the inequality. Once that's finished and you've solved for your unknown variable, you'll then be left with a solution set. And so, to this end, if we want to, say, add 5 to both sides, maybe I decided that I want my numbers on the right-hand side. I'm going to go ahead and move my 5 away. I'll use the additive inverse at this junction. I'll add 5 to both sides. I'm going to get a 0, and then we'll have 3y. 5 minus 2 gives you 3. 4y plus 0 is just 4y. We're going to go ahead and use our additive inverse of a negative 3y, and we'll add it to positive 3y to move our 3y from the right side of our equal sign to the left side of our equal sign. Our 3y's disappear, they go to 0, and you have 4y plus a negative 3y. Well, I have $3 of debt, but I have $4 in my bank account, so at the end of the day, once I'm done paying back my debt, I will be left with $1. 0 plus 3 gives you 3, so I've got y is strictly less than or equal to 3. And I should say strictly, y is less than or equal to 3. If we view this situation on a number line, we're going to have a number line that goes from negative infinity to positive infinity. Somewhere on the number line, there will be the number 0. To the right of 0, 3 will exist somewhere. And what this statement is saying to us is it's saying that y can be any value as long as it's less than 3, so, or equal to 3 for that matter. So y could be 2, y could be 3, because 3 would be less than or equal to 3. 2 would be less than or equal to 3. That would be true. 1 would be less than or equal to 3. That would be true. 0 would be less than or equal to 3. I hope you guys can see every number all the way to negative infinity would be less than or equal to 3. If we were to represent this situation using a bracket, we need to use a bracket pointing towards negative infinity in order to denote the fact that y can indeed equal 3. Using the interval notation, you might say that if you were starting on the left-hand side at negative infinity, the y could go all the way from almost being negative infinity, but not quite, because negative infinity is a concept, it's not a real number, and it could go all the way to positive 3, because y can actually be 3 for this to be a true statement. Let's look at another example. We're going to look at example 7 on page 153. On example 7, page 153 in your book, you have 4 times the unknown number plus 1 minus 2 is less than, strictly less than, 8x minus 26. These types of problems are exactly like the multi-step LEOV problem statements, where we're just looking to reduce it to a 2-step problem statement, and then from a 2-step to a 1-step problem statement. Now, as you're scanning through this equation, you'll note that you have a sequence of parentheses. The sequence of parentheses generally means that you need to do distribution. So go ahead, do distribution. You get 4x plus 4 minus 2 is strictly less than 8x minus 26. 4 minus 2 is 2. Okay. Now we have a collection problem, right? We have terms that are on both sides of our inequality operator. So we need to determine what side we want to collect all of our terms to. Now, traditionally, I like to collect all of my terms to the left-hand side. Just that's my tradition. But it really doesn't matter. And in fact, if you collected all of your terms to the right-hand side, that would actually save you some time. It does not matter which side you want to collect your terms. You just have to watch out for that additive inverse and make sure you're using the additive inverse correctly. Also, make sure that you're using the multiplicative inverse correctly, because if you don't, and you don't make a slight adjustment, then you are going to get a wrong answer. We'll talk about that here in a second. Let's go ahead. We'll collect our x values from the left-hand side to the right-hand side. I'm going to use my additive inverse. I'm going to add a negative 4x to both sides of my inequality. When I do this, 4x plus negative 4x, that's going to give me 0x. And on the right-hand side of my inequality, I've got 8x minus 4x. Well, that's going to be 4x. 0 plus 2, well, that's just 2. And I guess I should back up. 0 times x is just 0. And 0 plus 2 is 2. We now have a two-step LEOV. It's just that all of our terms have been collected to the right side of the inequality instead of the left side. So now we can use the additive inverse, and we'll add positive 26 to both sides of our inequality. So we'll have 2 plus 26 is strictly less than 4x minus 26 plus 26. 26 plus 2 gives you 28, and this is strictly less than 4x plus 0, or simply 4x. Now, at this point, I'll use a multiplicative inverse. I'm going to multiply both sides by 1 over 4. And you're going to get 4 over 4x is strictly greater than 28 over 4. 4 goes into 28 7 times, so 7 will be strictly less than 1 times x, or said another way, x is strictly greater than 7. Now, on a number line, we might represent this situation. We're going to give ourselves a big line. We'll go from negative infinity to positive infinity, put 0 on the line somewhere, put a 7 on the line somewhere, and your x value is going to be strictly greater than 7. So we'll use a parentheses to indicate strictly greater than. We're not going to actually be equal to 7, strictly greater than 7. And we'll shade everything to the right side of your inequality operator, going to infinity, because x could be, say, the number 8, x could be the number 9, x could be the number 10, x could be 11, so on and so forth, all the way until you get to positive infinity. Using the parentheses notation or the interval notation, we might say that x could go from 7 all the way up to positive infinity, but it's never actually going to touch either 7 or positive infinity. It's going to be a number that's between this interval or that's on this interval, but it'll never actually touch or reach 7, and it'll never actually touch or reach positive infinity. Now, a good heuristic for students to use is just the following. If you have x strictly less than some value a, you're going to have a line that ranges from negative infinity to positive infinity. You'll always have a 0 on the line, and your a could either be a positive number or a negative number. It'll just be on the line somewhere. You're going to have a parentheses, and you're going to be shading everything less than a. Similarly, if you were to use the open hole notation, you'd have a line going from negative to positive infinity. You'd have a 0 and an a on your line, and you'd have a open hole at A, and you would shade everything to the left. Finally, using the parentheses interval notation, your x value can range from negative infinity, which would be like the starting point. You can think of this like this is where we start from on the left-hand side. We're going from negative infinity all the way up to A. But x cannot actually be A because we have a strict inequality. What happens if x is strictly less than A? Well, if x is strictly less than or equal to A, sorry, not strictly less than, but conditionally less than or equal to A, you've got a number line just like before going from negative infinity to positive infinity. You'll have 0 on your number line. You'll have the number A. And again, A could be a positive number. If so, it would be on the right to the right of your 0. It could also be a negative number. If it was, it would be to the left of your 0. You just have some number. I don't know what A is. You don't know what A is. It's just some number. So when you get the specific problem statement, you're going to change the position of this A. But this key or this tool, this cheat sheet, will help you know and or remember which way you should shade your inequalities. So in this instance, we've got x is less than or equal to A. So we're going to use a bracket, and the bracket will be pointed towards a negative infinity because x could be everything that's less than A, but it could also equal A. Using the open hole notation, you're going to have a graph from negative infinity to infinity. There will be an A, a dot right at A. You're going to shade everything going up to A. And then similarly, you'd have negative infinity to A as your interval, but instead of having a parentheses, you would use a bracket. If you have x is greater than some value, you're going to have an interval from negative infinity to positive infinity. You're going to have a 0, A somewhere on your graph. I don't know where it is, if A is positive or could be also negative. But what's interesting here is that because it's strictly greater than, you're going to use a parentheses and you'll shade everything that is to the right of A. Using the open hole notation, you have negative infinity, positive infinity, a 0, an A. You're going to have an open hole at A, shade everything above it. For x is greater than A, you're going to have a sequence of parentheses. Because you're starting at A on the left-hand side, you would have a parentheses and an A next to the parentheses. You're going to have a comma, and then because you're going to positive infinity, you would have a comma, positive infinity. To denote that x could be any number going from A, whatever A happens to be. Maybe A is 10. So going from 10 all the way to positive infinity. Maybe A is 100, so then x would be going from 100 all the way to positive infinity. But note critically, x cannot actually be A. X can be everything up to A, that's above A, but it will never actually be A. The final possibility is that x is greater than or equal to some value, in which case you're going to have exactly the same graph from positive and negative infinity. You'll have a 0 and A somewhere on the graph. The only difference is that you'll now have a bracket facing towards positive infinity. Additionally, you'll have a line from negative infinity to positive infinity, 0, A, close dot, shade everything going to positive infinity. You're going to have an A, you'll have a bracket, an A, because that's your starting point. You're going from A all the way up to positive infinity, and a parentheses to denote that you can never actually get to infinity. I want you guys to copy this cheat sheet and have it ready for your final exam, because you will be given some of these inequality problems, and it would be a big shame to mess up when you really should have a cheat sheet available to you. I'll see you guys in class. Take care.